today's class, January 9, this is Friday, chapter 5, formation of our solar system and star formation theories in general. So the main idea here is to form a star. I mean, stars are not there forever, right? So if you look, in fact, let's go back to our normal perception. When you go outside and you see these dots of light up in the sky at night, we think of them as being there forever because, I mean, you see them today, you see them next year or 50 years from now. So apparently their positions don't change. Of course, get if you subtract daily diurnal motion and Earth revolution around the sun, their relative positions in the sky don't change. And we think of their brightness as being the same throughout our lives. So we have the tendency of thinking stars are there forever, especially in certain cultures. It is said that a creator or God or some entity create all of them, right? Which means they came out of the will or the power or the magic power of some entity, which means they come out of nothing. And this chapter is important because it gives you all the steps that lead to the formation of a star. So stars come from something, they fulfill something in the universe, they have some role in the universe, and then they die out. And I'm using the word or the verb die in a wrong sense because stars are not a biological being that exist biologically speaking, and they die, they disappear, right? So it's not like that. Stars are not organic living entities, but they do form out of something, they do exist for a while, and they disperse. So what make up the stars? What stuff make up the stars? Gas and dust. So our galaxy has large group of what we call giant molecular clouds. Let me bring the class notes of chapter 5. I might have some pictures there, might be easier to show what's going on. Let me see. There you go. So our Milky Way galaxy has several of these giant molecular clouds. They have several million solar masses. So if you take the mass content of the sun, multiply by a million, so efficiently you could form millions of stars like our sun, but it doesn't work that way. These giant complex objects, they are very thin, right? They don't have a large density because this gas is spread over very large volume. But if conditions are good, if conditions are just right, the density, the content in certain regions of these giant molecular clouds will allow for star formation, which means gravity force, which we learn in chapter 3. So gravity force kicks in, and it starts slowly but surely contracting this gas, forming cores. And that's what you see in this picture here, right? So you form these cores, and these cores, as the gas contracts and reduces its volume, it forces the molecules, the atoms, the content of it to collide more efficiently, and then temperature goes up. So as the gas contracts, as the cold gas contracts, collisions among molecules and atoms increase, and then temperature goes up. So you have all the pathways of star formation. Cold gas spread over very large volume, gravity kicks in, and it starts slowly contracting. And as contraction takes place, forming these cores, um, then eventually uh, the gas itself becomes self-luminous, becomes bright, and then astronomers can see them through telescopes, and then we call them protostars. Does that make sense? So that's the idea. So a protostar is a cold gas that has been subject to gravity forces and is contracting, and is cold, is huge, is large. And here's my first question that you should upload and turn it in for these assignments. What protostars are? Are protostars large and cold gas? I just said yes, that's the answer. Or protostars are small and cold, or small and hot, or huge and hot. Why protostars can't? Okay, that's the question. So what protostars are as far as size and surface temperature are concerned? Now, that's question number one for your assignment. So there are three questions that I would like to pose in these assignments. So the protostars can't be hot, and the reason is hot gas has also high pressure, and this outward pressure prevents gravity to efficiently contract and collapse, forming cores, right? So as the star forms, as contraction takes place because of gravity, gas pressure fights that, so that there is always some fight, some imbalance between gravity that pulls in and the outward force that arises from gas pressure that kind of fights gravity, right? So eventually those two forces will reach a balance, and I will show you when that happens. Now, in addition to having the gas rain in, the gas fall into a core, giant molecular clouds have also rotation. They have some embedded rotation, and you might see the word angular momentum associated with it, which is a physical quantity that gives position and rotation of cells, of gas cells, and astronomers can calculate this quantity and use that to predict outcomes, to predict when the star, or what's going to happen with the star around, or the gas around the star. But the main point is, as the gas contracts, since there is this embedded spin, this embedded rotation, as the gas contracts even more, this rotation also increases severity. And if you study physics, if you go to college and you decided to become an astronomer, one of the things you're going to learn and apply your physics knowledge of general physics is to follow the fall of a gas cell from any region in a giant molecular clouds all the way to the center part of where the star will be residing. So depending on the distance or the angle this cell makes with this axis of rotation here, the cell might fall almost straight towards the core, or if it's in a funny position, it might fall towards the equator, the equatorial region, and then follow, according to Kepler's law, follow and spiral inward all the way to the central star. So it depends. It's just nature follows efficient pathways in order to produce things. And what I'm trying to say is, one of the natural process of this, or one of the natural consequences of this rotation, is the formation of this circumstellar disk. See that? See the circumstellar disk? This circumstellar disk forms because of rotation. And one cool thing of it is, we are here basically. I'm talking to you. I mean, I'm not talking to you. I'm taping some lecture, right? So, and you are probably listening now because this circumstellar disk was formed, because the gas didn't run directly to the star all the way, because a circumstellar disk was formed. Because of that, let me show you a cool movie here. because of that, let me show a better display of this circumstellar disk.
The fading light of a flaring young star has shed light on a puzzle involving crystals.
Okay, so this is a simulation. It's not a real thing, right? It's a simulation of a star. The star is EX Lupi. It's a star that is observable in the southern hemisphere. We can't see it from here, San Jose, California. And this star is a young star. It's not a protostar anymore. It's called a pre-main sequence star. We are going to learn these terms next week. But EX Lupi is very active. But here in this animation is showing the circumstellar disk, which is the result of what? These giant molecular clouds collapse because of rotation and form the center star, we call pre-main sequence star, and a circumstellar disk of material around. See that? There is a sound here. I wouldn't like to have this guy talking. A second. Let's see if I can get rid of that. Okay. Okay, very good. So the rotation is taking place, and see if I can go forward. Nah, wait a sec. You should watch this video, but I just want to go, okay, to the animation. Look at that. So because this star has a lot of strong magnetic field, this magnetic fields kind of disrupt the disk at certain location, and then disk material falls, it still falls onto the star in high latitude regions. But why am I showing this animation to you? Because I want you to realize and to visualize this circumstellar disk, what that is. But basically, out of this disk material, future planets, future moons, future asteroids and comets will come by, will be formed, right? And as you can see, the disk itself has different temperature regions. So closer to the star, the gas disk is somewhat hotter than it is in the outer skirts of this disk, right? So somewhat cooler here than it is there. And because of this, crystallization of materials will give rise to different components in the disk. So closer to the star, because it's hotter, you might find more metal oxides and silicates than you find in the outer skirts, where you do find also metal oxides and silicates, but you might find also ices, lots of ices, giving rise to a segregations in the different types of planets, right? Closer to the star, you have terrestrial planets, planets that have solid surface, rocky type. And as you go to regions further out, the planets are liquid, like Jupiter, Saturn, or are more like ices, like Uranus and Neptune. Okay, so that's the difference. So think about this. By the way, this is my question number 2, just to check out and see if you like this animation. What is the name? What is the name of the star that I show in this segment? In fact, the name is EX Lupi. EX Lupi. And what's the name of the star, which is a pre-main sequence star, observable in the southern hemisphere, that I show in this assignment? It's a very simple one. I just want you to follow my display. Look at that. This is cool, huh? It's very cool. In fact, this video it shows the research done with a with the Spitzer telescope, the space telescope, and astronomers were able to explain why olivine, which is a mineral that formed on Earth, on our planet, at very high temperature and pressure, 2000 Celsius, under below Earth's surface, but you can find olivine also in around the circumstellar gas of these pre-main sequence stars. And how can this olivine be formed? And astronomers kind of narrow down the main process as being ultraviolet radiation that is radiated away from the central star when gas fall on it. But that's not the point I want to show. I just want to show the circumstellar disk around EX Lupi. Let me go back there. Anyway, so here another depicting the circumstellar disk being depicted in there. In these pictures, the gas is going all the way to the central star. This probably is not the case. Probably the gas is halted at a certain distance because of the stellar magnetic field, and this contraction keep on going, right? It keep on going up to the point the star becomes very much stable, and this stability arises because in the center part of the star, in the core of the star, fusion reactions start to take place. The temperature and the pressure are such that fusion reactions are enabled, and then 4 atoms of hydrogen will be fused into 1 atom of helium, giving rise to energy production, and this energy travels through the entire interior and make stability a real issue in the star, and the star stays pretty much burning hydrogen into helium for, in the case of our sun, for billions of years, right? 10 billions of years or so. And that phase is called main sequence. So a main sequence star is one that is undergoing fusion reactions in its very core. Our sun is a main sequence star, not our sun, the kid, right? I don't have a kid with you. I mean, our star we name sun. Again, be careful with my accent. Sun star, not sun kid. So our sun, our star, is a main sequence star and is burning hydrogen into helium constantly, and has been doing so for about 5 billion years, and it's going to spend another so much of that time in that process. Okay, so that is my third question of this particular assignment. What is the important process that goes on in the very core of main sequence star? It's called fusion reaction. And this is the third question that I'm asking. What is the important process that goes on in the core of main sequence star? Okay. Let me see what else is going on here. That's a good thing. I show you that, and pretty much that's it. Now, in star formation is not just a theory. I mean, it's a theory, but it has lots of abundant observations backing it up. In our own solar system, let me go to the beginning, to the first slide. In the solar system, if you look at a picture of a solar system, the planets are all kind of aligned as if their orbits were pretty much coinciding with the ecliptic plane, which is the orbital plane of Earth around the Sun. So as Earth goes around the Sun, defines a plane. Now all the other planets have their orbits with an inclination close to the ecliptic, right? A few degrees off, which means the material that formed the planets came out of something that was orbiting the Sun in the same direction. By the way, all planets, they go around the Sun kind of in the same direction. Let me show you this. Let me show you this. It's a cool comet right here. See a comet? See, all the planets, they kind of go around the Sun. They go around the Sun in the same direction, and they are somewhat inclined, indicating they all came, or suggesting they all came from the same circumstellar disk. Also, when you look at the planets themselves and the Sun, they all rotate in the same direction, indicating the gas that formed them were pretty much rotating in that, as we look down on the solar system, in a counterclockwise direction. There are sorry, somebody came in, but there are counter arguments and exceptions to this rule. And for instance, Venus rotates in a different direction because probably collision when Venus was formed. Uranus also is well tilted, but in general, when you look at our solar system, they all go in the same counterclockwise direction as we look from north down on the solar system. Okay. And if you keep going up to the point of showing the other planets, Jupiter, Saturn, Uranus, and so on, so on, so on, they all go increase the number of hours so you can see. Now we can see Saturn, Jupiter, Saturn, even better, right? And Uranus, and so on, and Neptune. See that? They all go in that same direction, indicating these planets formed out of a circumstellar disk. So those are the 3 questions. Please upload and let me know if you need anything. Thank you.